Dear students, under the lecture series on complex analysis, we are learning topics under complex integration. Here we have a very significant theorem known as Cauchy's integral formula. The statement of the theorem is let f of z be a function which is analytic inside and on a simple closed curve C. Let z naught be any point in the interior of the closed curve C. Then f of z naught will be equal to 1 by 2 pi I integral over C f of z divided by z minus z naught dz. So now we have to prove this integral formula. So as the first step, let us consider a closed curve capital C into which let us choose a circle C naught with center z naught and radius r naught such that the circle C naught lies in the interior of the closed region C. So let me put that into words. So now if you see here, we are considering a closed curve capital C. So this is the closed curve capital C. Now inside this closed curve, that is interior of C, we are considering a circle C naught. So this circle that we are considering is C naught. So this is the closed curve capital C and the circle is C naught with center at Z naught. So center of the circle is Z naught and the radius of this circle is R naught. So now if you see, the Z naught is the only point inside this closed curve C at which the function f of z minus z naught is not analytic, but it will be analytic in the region D consisting of all points inside and on C. So inside this and on the curve C, it will be analytic. So except in the interior of this circle C naught. That is, so I have put that into words here. So now this Z naught is the only point inside C. Okay, inside this closed region C at which the function f of z by z minus z naught is not analytic and hence is analytic in the region capital D consisting of all points inside and on C except the points interior to C naught. So having this, we know that if a function is analytic in a region, then the integral over any two closed curves in that region will be the same. So this is the closed curve C. So the integral of this function in this closed curve C will be equal to the integral of this function inside this closed curve, that is circle C naught. So therefore, the reason is because the function is analytic in a region. So since it is analytic in a region, then the integral over the two closed curves in that region will be the same. So let us write that. So if a function is analytic in a region, that is, we told that this function is analytic in the region D. So if this function is analytic in that region, then the integral over any two closed curves in that region is the same. So this implies that, so we have integral over C first we will take, the closed curve C, which function? This function. So f of z divided by z minus z naught dz. So this integral will be equal to integral over, so integral over any two closed curves in that region is same. So this is one closed curve, this is one closed curve. So the other curve is C naught. So C naught, the same function f of z by z minus z naught dz. So this function over two curves. So the integral of this function over two different curves will be the same, since the two curves are closed curves which is in a region that is analytic. So that is what we get. Now in order to evaluate this integral, it is enough if we evaluate integral over C naught. That is what we want to establish. So what we are going to do in the next step is we are going to evaluate this integral. In order to evaluate this integral, so I have taken and I have written it now. So therefore this integral will be equal to, now in this integral, in the numerator we have f of z. To this f of z we shall add and subtract f of z naught. That is, this integral we can also write as integral over c naught f of z minus f of z naught. So now we have subtracted. So if we subtract, we should also add the same quantity. So plus f of z naught, the whole divided by z minus z naught dz. So this is what we get. Now from this, we can now separate the integrals. That is, this term divided by z minus z naught plus this term divided by z minus z naught. So we will write it as two integral over c naught f of z minus f of z naught divided by z minus z naught dz plus integral over c naught. Now this is f of z. So f of z naught. Okay, this f of z naught divided by z minus z naught dz. Now this f of z naught is independent of the integral. So it can be taken out because the integral is with respect to dz. So therefore this will also be equal to, that is, integral over, we have this f of z by z minus z naught dz, that is integral over c. This one I am writing. So this is equal to integral over c naught f of z minus f of z naught divided by z minus z naught dz plus, now this f of z naught can be taken out. So f of z naught integral over c naught dz by z minus z naught. Let us mark this as equation 1. Now in this equation we have two integrals to be evaluated. So this is integral, first integral, and this is the second integral. So we shall find each of them separately and we shall substitute them. First let us find this integral, that is integral over c naught dz by z minus z naught. So let us first evaluate this integral. So now we shall evaluate this integral. Now we know that C naught is a circle. So since C naught is a circle, and what is the center of the circle? It is Z naught, and the radius of the circle is R naught. So with center Z naught and radius R naught, we have, so we know that if the radius is at the origin, that is, if the center is at the origin, then z will be equal to r multiplied with e power I theta, where r is the radius. Now here the center is at z naught. We can write z minus z naught because the center is at z naught. If it is at the origin, it will be z minus 0 equal to r e power I theta, where r will be the radius. But here the center is not the origin, it is at z naught. So z minus z naught is equal to, the radius is what? R naught. So it will be r naught e power I theta, where theta will range between 0 and 2 pi because it is a circle. So the limits for theta is between 0 and 2 pi. Now differentiating on both the sides, what you will get? Differentiation of z is dz. This is a constant, it will become 0. R naught is a constant, so it will come as it is. Differentiation of e power I theta is I multiplied with e power I theta. Because for e power I theta, it is e power I theta. And we have to multiply with the constant here, which is along with theta. So I e power I theta, and the differentiation of theta is d theta. So now we have z minus z naught dz, all this we will substitute in this integral. So this integral will be equal to integral over the circle c naught. So what is the limit for theta? It is 0 to 2 pi. So 0 to 2 pi. And then what is dz? Dz we have obtained it here. So that we have to take and substitute. So r naught multiplied with I multiplied with e power I theta d theta divided by z minus z naught is what? R naught e power I theta. Now this r naught and r naught gets cancelled. E power I theta and e power I theta gets cancelled. I is a constant which can be taken out. An integral between 0 to 2 pi d theta is what remaining we have. And what is integral d theta? It is theta. So I multiplied with theta and between the limits 0 to 2 pi. Now we have to do the upper limit minus lower limit. So when you apply the upper limit, you get 2 pi minus the lower limit is 0. So that is equal to 2 pi I. So this is what we get for the second integral, that is integral over c naught dz by z minus z naught is 2 pi I. So in this equation 1, we have evaluated the second integral. Now we shall evaluate the first integral, that is integral over c naught f of z minus f of z naught divided by z minus z naught dz. Let us evaluate and we shall substitute both the integrals in equation 1. So let us evaluate this integral now. So now in order to evaluate this integral, now first we shall try to understand some concepts. First we know that f of z is analytic. So now since this f of z is analytic, it is by the theorem we have understood this. So if a function is analytic, then we can say that that function is continuous. So f of z is continuous. What do you mean by that? When do you say that this function is continuous? One of the main concept is existence of the limit. So if a function is continuous, we can say that limit exists for that function. So this implies limit z minus z naught of f of z is equal to f of z naught. So this is the reason, because it is continuous, it also implies that the limit exists for this function. So if the limit exists, then we can write the derivative. That is, we can write that. So hence, I will write here, it is the continuation of this. So hence, limit z tends to z naught f of z minus f of z naught by z minus z naught. Because it is analytic, the derivative exists and it is equal to f dash of z naught. This is by the formula of the derivative which we have seen in our previous lectures. So we can write this. So now what we shall do, let us take this function as g of z. So let us consider g of z to be equal to f of z minus f of z naught divided by z minus z naught, where z will be not equal to z naught. Now this function will be defined. So since the limit exists, so this function is defined. The reason is the limit of this function exists. Okay, since the limit exists. Now if g of z is equal to this, then we can define g of z naught is f dash of z naught. So this will imply, because of this we can say that g of z is analytic at z naught. In fact, we can say that g of z is analytic inside and on the circle, inside and on the circle C naught. Now here we are going to make use of Cauchy-Gorset theorem, which we have learnt previously. So let me first give the statement of that theorem. So using this theorem, We know that if g is a function which is analytic at all points inside and on a simple closed curve, then integral over c naught, that is integral over that curve g of z dz, will be equal to 0. Now using this, we know that here g of z is analytic inside and on the curve c naught. So therefore we get integral over g of z, integral over c naught, g of z dz is equal to 0. This is by using this theorem, that is Cauchy-Gaussian theorem. Now this will imply integral over c naught. What is g of z? We have defined g of z already. That is it is f of z minus f of z naught divided by z minus z naught. So using that, we have here f of z minus f of z naught divided by z minus z naught dz. Now since this is equal to 0, after substituting g of z, we see that this is also equal to 0. Now we shall make use of these two integrals, that is this integral, and previously we have found this integral. So this integral we have evaluated already. It has been evaluated to be equal to what? 2 pi I. So the value of this integral we have evaluated as 2 pi I. So this integral. And then now we evaluated that this integral, value of this integral was equal to 0. Okay. Now we are going to make use of these two integrals, this and this, where in equation 1. So this integral is 0 plus f of z naught multiplied with, what is the value of this integral? It is 2 pi I. So we shall substitute that. So equation 1 on substituting these two integrals will turn out to be f of z naught to be equal to 1 by 2 pi I integral over c f of z divided by z minus z naught dz. So on applying both the integrals, we get the value of f of z naught to be equal to this. So hence the theorem is proved. So the evaluation of both the integrals is very important, and its substitution leads us to the Cauchy integral formula. So I hope you would have understood this theorem. Thank you.